Some common applications of using the derivative involve distance or position, velocity, and acceleration. In this lesson, we're going to start with some position and acceleration velocity kind of problems and talk about other applications of derivatives using equations that are meant to model something in real life. So our first example, suppose you were to jump off the CN Tower. That is jump, not just fall off the CN Tower, not a recommended activity, of course. Your position above the ground might be given by the equation that you can see here. Okay, obviously a quadratic equation, ignoring air resistance. And if we think about the graph here, this curve would probably look, we know it's a parabola that opens down, it likely looks just something like this right here, where the x-axis is t for time, and the y-axis is s of t, which we're calling your position above the ground. It is common to use S for position in a physics question like that. So notice that the time here is in seconds. And our distance is, of course, in meters. The first question says find the average velocity over the first 3 seconds. So something that you might remember from earlier in the course is that average rate of change is the slope of a secant, and that's exactly what we have here. So we're basically looking at the slope of the secant from 0 seconds, which is right here, to 3 seconds, which is probably somewhere in here. Okay, so to do that, we're going to figure out your position at s of 3 seconds, subtract that from s of 0 seconds, and divide by 3, the run. So basically looking at calculating the slope from here to right in here. Okay, we know that that run is going to be 3, and we know that the rise will be the height here. Sorry, the height here, s of 3, subtract s of 0. Now, if you plug in t equals 3 into this equation, you will find that you end up getting 422 meters. If you do that, I'm not going to include that work here. And then s of 0, you can see that that's clearly going to be 460 divided by 3, which gives you about negative 12.7 for the slope of that secant, that red line. Clearly it makes sense that it is negative, and that's your average velocity over the first 3 seconds. Now let's also think about the units here too. We're talking meters when we talk about the 422 and the 460, and we're talking about seconds here. So the units do give you meters per second. So over the first 3 seconds, your average speed would be about negative 12.7 meters per second. Okay, next, we're going to look for the instantaneous velocity after 2 seconds. Now, the instantaneous velocity will be the slope of the tangent line. So we're talking about s prime of t. So s prime of t is equal to, if I take the derivative of this quadratic, I get negative 9.8 t plus 2. So that gives me the slope of the tangent at any point on the curve. I want to know at 2 seconds. So s prime of 2 is negative 9.8 times 2 plus 2, which gives you negative 17.6. And again, our units are meters per second. Because when we do derivatives, you have to think about first principles. You're doing a limit question that looks a lot like finding the slope of the secant. The limit is h approaches 0 of f of x plus h minus f of x all divided by h. Well, the f of x and f of x plus h in this example will be in meters, and the h value is going to be in seconds because it's talking about the run along the graph. So the units work out. And I'm only stressing the units because when you're working with any equation, you need to understand that thinking about secant lines helps you get the units that correspond to the derivative, in this case meters per second. Now find your velocity at any second t. That's the answer that's already up there. That's just the equation. S prime of t is equal to negative 9.8 t plus 2. Now we often call that v of t. So v of t is equal to s prime of t, which is negative 9.8 plus 2. What about your maximum height? What is that? Well, we've talked a little bit about turning points, okay, unless you've started this lesson early. And we know that there is a turning point right here where the horizontal, where the tangent line at that turning point, we know that the tangent line has to be 0. The slope of the tangent has to be 0. Now, we talk about in other lessons that just because there's a horizontal tangent line doesn't mean that there's a turning point, but we know that this is a quadratic equation. We know it has a turning point. So we know that, you know, at some place the dirt is going to be equal to 0, and that's going to represent the turning point. That's just because we know parabolas that open down look like that. So figuring out the maximum height, we just are basically saying, well, when is s prime of t equal to 0? Which is the same as saying, obviously this right here, but it's the same as saying when is your velocity equal to 0. So if you're to jump off into the air, the maximum height happens when your velocity hits 0, because then your velocity obviously becomes negative and you go down. Okay, positive velocities in this example would represent going up and negative velocities going down. So just solving this equation does give you about, the answer is not super important, but about 0.204 seconds you hit your maximum height. Okay, so we came up with a velocity function, which was the same as s prime of t. And of course, we called it v of t, negative 9.8 t plus 2. And now we're asked for the rate of change of our velocity function, which is again just asking for the derivative. So let's look at v prime of t. That is just going to be negative 9.8. What does that represent? Well, that's the rate of change of velocity. Well, there is a special name that describes the rate of change of velocity, and that's called acceleration. So this represents the acceleration, and it's a constant value, and you might know that, okay? The acceleration due to gravity is 9.8 meters per second, or 9.8 meters per second squared. If you jump off the CN Tower, every second your speed will increase by 9.8 meters per second. That is v prime of t. We sometimes call that a of t. We also sometimes call it s double prime of t, because by the time we've gotten to this point, we've actually taken the derivative twice. And we refer to that as what's called the second derivative. So this here is the second derivative. And in prime notation, we just add an extra little dash there to say s double prime of t is s prime of t and the derivative of the derivative, or the second derivative. There's a lot of coming up in this course about second derivatives. This is just a very brief introduction to it using acceleration. Now, how about the units here on acceleration? I told you the units are meters per second squared, which is the same as meters per second. How do we get that? Well, remember our original graph had s and t. So we had meters and seconds. That's the original graph. Then we took the derivative to find the velocity graph. Now, the velocity graph still has seconds, s for seconds, but its y values are in meters per second. So the velocity graph, which is this one right here, it's actually a straight line that goes down. Okay, its rate of change is meters per second divided by second. So meters per second divided by second, which gives you the meters per second squared. In this next example, we're talking about the position of a dragster, so like a race car. And given by this equation, which is a cubic, where t is greater than 0, s of t is the position of the dragster in meters from the starting point, and t is time in seconds. So the first question says, after how many seconds does the dragster come to a stop? Well, when do you stop? Your velocity is equal to 0. So we're looking for when v of t is equal to 0, which is the same as saying when is s prime of t equal to 0. So s prime of t is v of t. The equation for that would be 12t, taking the derivative now, minus 3/5 times t squared. So we're interested in knowing when is that equal to 0. So when does 0 equal 12t minus 3/5 t squared? I can factor the t out, and I'm left with 12 take away 3/5 t. So we have t equals 0. That's not a surprise that at time equals to 0, our velocity is equal to 0. And also at 12 minus 3/5 t equals 0, which means 3/5 t equals 12. Okay, multiply both sides by 5, and you get 60 divided by 3, you get 20 seconds. So the dragster is at a stop at 0 seconds and at 20 seconds. Now, whether or not the person asking this question cares about the 0 seconds, I don't know. But we know that those are definitely when the dragster isn't moving, the velocity is 0. The next question asks about the maximum velocity. So, I mean, one thing we could do is we could look at the graph of this if you like, and I will throw this in Desmos, and I'll show that to you now. So there you see the graph of this dragster in seconds, or sorry, in Desmos, and I've adjusted the scale quite a bit, obviously, to get everything to fit in. Now, notice, of course, our answers make sense here. The velocity is 0 at 0 and at 20. You can see the horizontal tangent line, meaning the rate of change is equal to 0 at those points. That would be true even if these weren't turning points. They still have a velocity of 0, since the tangent line is clearly horizontal. Now we're asked for the maximum velocity. That does not mean we're looking for this point right here. This is distance. This would give you the maximum position the dragster has. Okay? I don't know how. The dragster must be coming back to the starting line somehow or something. I'm not sure what's going on here. It doesn't really matter. But this isn't the graph that's going to give us the answer to that question. What we can do instead is we can say, okay, the maximum velocity, if you want to know the maximum of a function, okay, any function, any curve, you can look at its derivative and see when its derivative is equal to 0, and that's a possible maximum value. So what we need to do is we need the derivative of the velocity function. So we actually need to look at the acceleration, or v prime of t. V prime of t, we take the derivative of this equation that we used up here, is going to be 12 subtract 6/5 times t. Okay, so I'm taking the derivative of the velocity function. Now the velocity function actually is just a parabola that opens down. That's the velocity. The maximum velocity is the turning point of the parabola. Now I know that this curve must have a turning point. So when you're working with parabolas, it's nice. There's no need to verify a turning point. I know that there has to be exactly one turning point, exactly one place where the tangent line is horizontal, and I know it happens whenever this is equal to 0. So set that equal to 0 and solve for t. Okay, you will get, let's see, 6/5 t equals 12. That's going to give you t equals 10. So the maximum velocity happens at 10 seconds. Now the question, it asked you for the maximum, it doesn't really matter. V of 10, just find V of 10, that's the answer. I don't care about the answer. Okay, plug in 10 to the velocity equation, and there you go, you'll get your answer in meters per second. Now in this last example, we have an equation where C represents cost and X represents number of items produced. And let's just start with the very first thing we're asked to do, find C prime of X. So it's a polynomial function, not too hard to take its derivative. C prime of X will be equal to 1.26 minus 0.02x plus 0.00021x squared. Sorry about all the zeros there. It requires a little bit of work to count those. And there you have it. So this C prime of X is actually called the marginal cost. Based on what we know about calculus, what must that represent? So maybe I don't know anything about economics, but I know quite a bit about calculus. And actually, I do know a bit about economics. I took a few economics courses in university, and I got to tell you, if you know calculus in a first-year economics or even a second-year economics course, it can be very helpful. It can make solving a lot of questions a lot easier. In any case, what must this derivative represent? Well, the original graph had C for cost, so we assume that that's in dollars. Okay, and X items, so in items. So the derivative represents the rate of change of this graph, which is kind of like the slope. It's dollars per item. So the marginal cost must represent the cost per item. And so what they actually say about marginal cost, so they talk about that, is the increase in price if you want to produce one more item. So it's the cost kind of the net. You could think of it as the cost, increased cost. I will put the word increased in there. Increased cost of the next item. That is what a marginal cost is. So it's like when we talk about marginals, we're usually referring to the increase in something. In this case, the increase in cost if you produce another good. Obviously, it costs more to make more items, but sometimes the increase between 10 items and 11 items is different increase in cost than 100 to 101. Could be 10 to 11 doesn't cost that much more, but 100 to 101 costs a lot more for some reason, or the other way around. And this thing says find the marginal cost if 10 units are produced. Well, that's just C prime of 10. And if you do the math there, you should guess, you just plug it into this equation here, and you should get, I've got $1.081 per item. So that's kind of like the instantaneous, or the increasing cost if you go to produce the 10th item. You're looking at 1.081. Okay, suppose the company wants to minimize marginal cost. What should their production be? Well, if they want to minimize marginal cost, then we're looking at finding the min value of C prime of X, not of C of X, but of C prime of X. So we again need to look at the next derivative to figure that out. So there's C prime of X. We need to take the derivative of that. So C double prime of X is going to be, equal to 0.02 plus 0.0042x. Notice that every time you take the derivative, you go down a degree. So original function, cubic. First derivative, quadratic. Second derivative, linear. If you looked at the derivative past that, you get a constant value. Okay, so degree 3, degree 2, degree 1. You could keep going. There's such a thing as a third derivative. Now we want to know when that is equal to 0. So we think about C prime of X, and C prime of X is just a parabola that actually in this case opens up. So C prime of X just looks something like, this right here. Okay, a parabola that opens up. That's C prime of X. So we know that it has a minimum. Okay, we know that this minimum exists, and we know there's exactly one turning point. There's exactly one place where the tangent line here is horizontal. Okay, and we know that that must be when this is equal to 0. So unlike the lesson on turning points, where it's really important to verify turning points, in this case, we know that there has to be a turning point here. Okay, because we're just basically asking to find the turning point of a parabola. To find a turning point of a parabola, just find the derivative, set to 0. That gives you the turning point. If you remember completing the square and doing stuff like that in earlier grades, it's pointless now. You just use calculus. It's much, much easier. We don't need to verify that we've found the vertex of a parabola because there's only one and there's no other place where this tangent line is horizontal. I apologize if I've said that a few times. Okay, continuing with this example, we just solve for x. And I'm getting about 47.6 will produce the lowest cost per item, or the lowest marginal cost. So we don't know what that lowest marginal cost is. We could find it if we just put in 47.6 into C prime. Okay, so there's that's the answer to the question. What should their production be? 47.6, and then the lowest marginal cost occurs at C prime of 47.6. The total cost occurs at C of X. And there you have it.